Can you see my screen, students?
Yes.
So today's class will be related to elastic and plastic deformation, because theory of metal forming all depends on this plastic state, and as it is in plastic state, we can deform it permanently. So we have to know that when the plastic state will be there. So when energy goes into changing the shape of some material and it stays changed, and that is said to be plastic deformation. We'll put stress, and because of that stress, it will be deformed, and it will be deformed permanently so that it will not go back to its original position. That is known as plastic deformation. And when the material goes back to its original form, that is elastic deformation. So two regimes, elastic and plastic. And two regimes separating is the yield strength. If you've gone beyond yield strength, it is a plastic deformation. Below yield strength, elastic deformation. Why we are going for hot forming another part of it, so that the yield strength is less, we can put more effort and we can deform easily. But if it is in room temperature, cold state, then the yield strength is more, but there are some advantages of cold forming. But the problem is that huge amount of force, and sometimes it gets cracked. So a judicious decision has to be taken that whether we'll go for cold or hot, depending on the material or alloy we are dealing with. So mechanical energy is lost whenever an object undergoes plastic deformation. So all this energy is expended in order to deform a material or metal in plastic form. Let me find out how many students have joined. How many?
15.
15. So that is the state. So my efficacy is in that state, but 15 is not a bad number, because if I definitely want only the interested people to be in the class. So this is stress, this is strength. Stress, you know that, calculated force by unit area. Stress is if a force is given, and in the reactions, what the force is returned back by on the basis of Newton's third law, and that is divided by area, it will come stress, and strain is dimensional change in terms of stress. And here it is the linear one where stress is proportional to strength up to yield strength, and the proportionality constant is that, and Young's modulus is the proportionality constant. So that is the slope, and that is this modulus will be calculated in this very way, the ratio between the rise and the run. And this is yield strength, and then it goes for permanent. We'll be dealing with that, but in this region, it is ultimate. And then it will start coming down with some necking. And this is a strain hardening state. Please remember, this is a strain hardening. Because of these strains, the molecules and all those things are getting compacted and the surface area, and it is getting strain hardened. That is the advantage of cold forming. If you do all those things in lower than the recrystallization temperature, then the material will be consolidated here. Li will be consolidated and hardening will be there. So cold surfaces are much better surfaces, cold rolled surfaces or cold form surfaces, because of the hardened one, and your hardness will be more and surface finish will be great if you do it in the cold form. And this is the ultimate one, and then it will again come back, and ultimately it will fracture. Where necking will be there, I will show you in a YouTube video in a tensile testing sample how the necking occurs. Is it clear, student? And these you cannot forget. You cannot forget the stress strain curve. throughout your life as a mechanical engineer. Any questions? Next. Am I audible?
Yes.
Yes, sir.
You see, again, it is the toe region, a little bit of non-linearity is there. And after that, to this proportional limit, you will find it out. This is the linear region. And after that, up to yield point, if you can divide it in a expanded way, you will find it out. After one point, below yield point, you will have little non-linearity, and after that is the elastic limit. Beyond that, the Parman deformation will be there, a little bit of these kind of movement, and after that, it is absolutely the permanent deformation. And then in between that, we have to work. And this is the ultimate one, and then it will come back as a rupture point. We cannot go to that limit because there is a possibility of then again coming back, and possibility of rupture will be there. So this is again a little bit of differentiation. This is proportional. Problem is with these kind of non-isotropic material like rock and other things, this is not linear. And that is why difficult to predict in case of non-metals and ceramics and the rock related material, ceramic material, and there lies many non-linearity, and that is difficult to model. Any questions?
Sir, plastic deformation occurs beyond yield point.
And beyond, truly speaking, beyond elastic. So there is a small region between the elastic limit and the yield point. A small region is there, a little bit of slope changes. And after that, after this elastic point and this, after that you can tell, yes, but elastic point limit is this. There also it initiated, but truly speaking here, our working of metal forming will be here. But very consciously, below that, because then the possibility will be there, the rupture. I will show you in the YouTube video. So this is the case. It is expressed in Newton per millimeter square, force by unit area. This is the elastic region. This is the plastic region. And there is the fracture. And strain is represented in terms of the percentage. Elastic limit, and their non-linearity and all sorts of things will come. And then you will have this highest point is tensile strength. And this is our zone of operation, plastic deformation, but definitely in this side, not in this side, this side. So, and here is the elastic deformation. This is the flow region. It starts flowing. So we have to calculate these flow stresses related to that, and that is relevant. And where you will have these flow stress is equal to K into epsilon to the power N. Epsilon is the strain and N is the strain exponent. And that way we will calculate. I will give you some numerical examples also. And here the strain hardening will be there. Because of this flow, there will be some consolidation in the surfaces, and that the surface will be hardened surface. Difficult to do some scratching, and this portion is known as strain hardening. And because of that thing, sometimes after machining, you have to go for stress relieving operation. You harden the surfaces, and sometimes it is not needed because some stresses will be generated associated with that. And in many cases, you don't want that stress has to be relieved. In case of machining of the structures, one has to do some stress relieving operation and then go for the next machine cut. Why? Because if the stress is not relieved, it will be relieved some point of the time. And if all those structures, there are holes and alignments are important in order to put some shaft there, there is a chances of bending. So you have to stress relieved. And if it is a very big structures, you have to put it into the open field under the sun, heat and dust. For some time, the stress will be relieved, and then you go for the machining. So this is, and that is also occurs whenever you are going for some kind of welding. So after doing things, then you have to put it in stress relieving, then weld, then stress relief, then weld, that stress relief, and that is required for your very precise structures of machines. And that I only know because I was exposed to heavy machine building division. And we have burned our fingers. Why I'm chasing with those vendors in Sheffield of Bengal, that is Howrah, Ichhapur, water tank and all those areas. And why you cannot give? Sir, we have to do these stress relieving operations, getting the furnace free and stress relief, and then again welding or machining. That took a hell lot of time. So that informations and other things not easy to appreciate whenever you are a student, unless you're burning your fingers in terms of manufacturing all those things. With the vendors, things don't become clear. So undeformed molecular structures and there. And whenever elastic deformations are there, suppose it is in a tensile testing machine, you are doing this, and when plastic deformation, there are slips. There are slips because of this tensile load. Slips. This is a slip plane, and that slips, and that is why the permanent deformation, whenever slip occurs, permanent deformation. That is the theoretical explanations of why it is happening beyond yield strength. Some slips occurs. So molecular orientation and other things just jeopardize. So it is a permanent deformation. Student, is it clear?
Yes.
So the yield strength depends upon the bond associated with that. Whenever you can give enough force so that you just force this slip to occur, so that will determine the yield strength. So molecule to molecule, alloy, whatever the strength is there, and that depends upon how much force is really required in order to inflict this slip. And this is the slip plane. So you can see the elastic, this is the proportional elastic. It is going there and coming back, going there and coming back. Sorry, going there and coming back. Elastic deformation, little bit of shifting, but no slip. Little bit of shifting, no slip. And whenever you gone for this yield strength, and here you are in the plastic region, elastic plus plastic, elastic plus plastic. So little bit of disorientation, linear disorientation, layer by layer, and little bit of slip. So elastic plus plastic, elastic plus plastic. And beyond that, it is stress is removed, plastic, total plastic, slip occurs. And that is the very good representation. And this is the plastic strain, permanent change in the dimension. We are interested about that. Plastic strain that will determine the formability of those metals and alloys. Very good representation. Elastic deformation, elastic plus plastic, and it is totally plastic where slips permanently occurred. It will not go back to its original dimension, and this is plastic strain. Is it clear, students? And this you appreciate throughout your professional career if you are in the engineering profession. So initial, I have already told, initial bond stretch and planes share, place and share. The shear forces and other things will be occurring there in terms of the molecular positions. Small load, higher load, planes still shared, permanently shared. Elastic plus plastic, linear, elastic, and then you come back. but it is the plastic strain. Plastic means permanent. Plastic means permanent. And that is, we are interested about that. We are interested about this plastic domain. So the difference between elastic and plastic deformation process, it is elastic, it's deformation which disappears on removal of load, disappears. But in case of plastic, it's permanent, which exists even after the removal of load, permanent. So I want you to deform plastic way, so that your impression of understanding and knowledge will deform your mindset permanently towards the knowledge enhancement region. So the elastic, it is the beginning stage of deformation, initial. The plastic deformation after the elastic deformation. After this elastic zone is over, then and then only the plastic zone begins after the yield point. Clear? It is reversible, obviously, because it takes place over a short range of stress strain curve and comes back. That is why reversible. It is irreversible, takes place over a wide range. It is a small range, wide range. I can show you all those things in terms of a YouTube video. It is irreversible and takes place over a wide range of stress strain curve. After elastic deformation, plastic deformation starts, obviously, and after plastic deformation, fracture starts. So which is after elastic? Plastic. After plastic, fracture. The elastic deformation is favored by lateral longitudinal shear strengths. Lateral, longitudinal, lateral and longitudinal, and all those things are the shear strengths. But here, sleep and twinning. Sleep and twinning, I will explain that. Sleep and twinning, this is the phenomena. Here, lateral, longitudinal, and shear strain. Here, sleep and twinning will occur. And what is flow states? In material science, the flow stress typically denoted as Y suffix F and defined as the instantaneous value of stress required to continue plastically deforming a material to keep it flowing. So in plastic state, some kind of flowability will be there. The definition of fluid is what flows. In plastic state, under the load, the material also flows to some extent, though have significant shear stress. In case of fluid, it is negligible shear stress. In case of superfluid, the shear stress value is close to zero. The fluid becomes container independent. We can get in superconductors fluidic state so that the magnetic levitation will occur. If we can go for the cryogenic state, our magnetic levitation trend can occur with minimum energies. So tomorrow's magnetic levitation trend will run with minimum energies. So intercontinental travel will be as less costly as going from IIT ISM Dhanbad to Hirapur or railway station. So here the material flows in the plastic region, and flow stress is associated with one constant and strain to some exponent. This is the formula. So K is the constant and N is the exponent, depends on the material or metals. Metals behavior is expressed by the flow curve. So the flow curve, as it is an exponential one, these curves will behave like this. K is equal to the strength coefficient in megapascal, strength coefficient. N is strain hardening exponent, depends on the metal alloy. Stress and strain in flow curve are true stress and true strain. In the flow curve, it is true stress and true strain. So whenever you are explaining that thing. So in this first section, uniform straining up to the ultimate strength level, and after that, making will occur. So engineering strain, this is, and the exponent behavior of this thing, it is true strain. Engineering strain, true strain. Engineering strain where it is following these equation. and true strain, a true strain and engineering strain is this. So what is slip and twinning, which is occurring in the plastic regime? The shear deformation which moves atoms in one crystal plane over the atoms of the other by much atomic distance relative to their initial positions. Lot of distance, lot of distance is generated because of the slip, and that is known as slip. And what is twinning? The shear deformation in a crystalline material through a process by which a portion of the crystal takes up orientation, which makes that portion as a mirror image of the parent crystal. Twinning and morphing, that is also important in computer graphics. And here, that means one image is that percolated to the other part of it, in so that way it is there. So it will be twinning. I think I'm spelling mistake is there. It should be one. It requires lower stresses, it requires higher stresses. A threshold value of stress called critical resolved shear stress is required for slipping to take place. So in the plastic way, you have to deal with whenever we are going into the deeper part of metallurgy, we have to find it out what is the critical resolved shear stress required for slipping. And there is no such threshold value of twinning to take place. But slip, there is a threshold value. Slip band is formed after several milliseconds, and twins can form in a time as short as few microseconds. Slip occurs in milliseconds, twins occurs in microseconds. It involves the shear displacement. Whenever metal cutting also, it is a shear force. Shear displacement, angular displacement of an entire block of the crystal. Here, every atomic plane is displaced by definite distance, and a uniform shear strain is developed. Every atomic plane. Here, maybe some plane can be left alone, but here every atomic plane will be there. So that's all. Now, any questions, student? Then I will show you. Some YouTube video. Let me go for that. No, it is. I want to show you. I don't know whether it is Hindi or not. Okay. Can you see that, students?
Yes, sir.
Yes, sir.
In this, we have considered mild steel. It is a ductile material. For tensile test, always you have to consider the ductile material. In this case, we have considered mild steel. This is the given specimen. If you see the specimen, here threadings are done on the specimen. These threadings are done for the grip purpose in the UTM machine, Universal Testing Machine. Okay. Before we start conducting the experiment, initially you should note down some of the things. The diameter of the specimen, gauge length has to be calculated, and the parallel length has to be calculated, or it should be noted. Okay. And before I start conducting the experiment, you should know why the tensile testing specimen is done, or through this experiment what you are going to obtained. Once you are going to conduct the tensile test on a mild steel specimen, we are going to find out the percentage elongation in the member. When you apply the tensile load on the specimen will elongate. There will be increase in length of the specimen, whereas the diameter of the specimen decreases. You need to find out the percentage elongation in the specimen, and you need to find out the decrease. As I told you, there will be decrease in the diameter. You need to find out the reduction in cross-sectional area, and you need to find out the Young's modulus of the specimen. During the when you start taking the reading, in that you need to once you draw the graph, you need to note down the percentage elongation, and you are going to find out the yield stress, ultimate stress the specimen is going to take, and after that we are going to observe the neck formation in the specimen. After the neck formation, you will see a small crack on the specimen, and that crack will propagates, and ultimately the material will break into two pieces. You need to note down the fracture point or the load at which the specimen fractures. This is how the experiment is conducted. Now I am going to note down the initial diameter of the specimen. Close the doors. Here, by using the vernier scale, you need to find out the diameter of the specimen. Now I am going to calculate the diameter. Here you can see that the diameter of the specimen is 18 mm. You can see the point. It is the specimen diameter is 18 mm. You need to note down the specimen diameter as 18. Now I am going to find out the parallel length of the specimen. By using the vernier scale, I am going to find out the parallel length of the specimen. Close the doors. Now you can see that the parallel length of the specimen is 170 mm or 17 centimeter. The parallel length of the specimen is 17 centimeter or 170 mm. Now this is the sketch of the specimen. In this we have measured the parallel length. The parallel length of the specimen is 170 mm. You need to note on that. And we have measured the diameter of the specimen. The diameter of the specimen is 18 mm. You need to write down. Now we have noted on the diameter of the specimen. The diameter of the specimen is 18 mm. D is equal to 18 mm. The original cross sectional of the specimen. Substitute the diameter 18. You will get the original cross section of the specimen. Now original gauge length. It is gauge length is equal to 5 into D. D is 18. 5 into 18 is 90 mm. The gauge length we have calculated as 90 mm. Original parallel length we have calculated as 17 centimeter. Here you have to convert it into mm. It will be 170 mm. Now I am going to make the punching marks on the specimen. Here the gaps between the two specimen I will make it as 1 centimeter or 10 mm. Okay, like that you need to mark those things after that by using the punching. Now you have to make the punches on the specimen by using the punch and the hammer. Whatever the marking you have done, on that you need to make the punches. Here you can see that already I have done the punch mark on the specimen. Here you can see that these are the punch marks on the specimen. Now I am going to take this specimen and load it in the UTM machine, and you need to note down the values. In this tabular column, you need to note down the load. According to the load, how much extension is there in the specimen, you need to note down. Similarly, these are the load applied on the specimen. The interval or the we are going to apply 10 kilonewton, and as a result of that, how much elongation you are going to observe that in the specimen, you need to note down. In this initially readings, we are going to take it from the extensometer to the specimen. We are going to attach the extensometer. Why extensometer is used? It is used to note down the elongation in the specimen. In the UTM machine, we have a machine scale. Through that also we are going to note down the elongation in the specimen. But initial loading, the elongation in the specimen will be like 3 into 10 raised to minus 2. It is difficult to measure that in the machine scale. For that, initially we are going to note down the elongation in the specimen using the extensometer. Once it reaches the maximum load, at that time we are going to remove the extensometer. After that, further elongation in the specimen will be taken using the machine scale. Once this loading has to be continued until the specimen fails or the specimen fractures. You need to note down the elongations. Once you are going to obtain the elongation, after that you need to find out the stress and strain. Stress is load divided by original cross sectional area. If you apply 10 kilonewton load, how much stress you are going to observe? Therefore, stress is equal to load divided by area. Load unit is Newton, area is mm square. Therefore, unit of stress is Newton per mm square. Whereas strain is change in length to original length. This is the elongation, and how much change in length you are going to observe. You know the original length of the specimen. From that you are going to obtain the strain. For example, for 10 kilonewton load, stress is equal to 10 divided by cross sectional area, pi by 4, diameter is 18 square. From this you are going to obtain the stress. Like this you need to calculate it for each loading 20, 30, and after that you need to draw the stress versus strain graph. From that you are going to obtain the yield strength in the material, ultimate strength. Similarly, at this particular point, when it reaches the ultimate stress, neck formation takes place, and at this particular point the material will breaks into 2 pieces. After the loading, you need to note on the specimens after testing. This is final diameter of the specimen. Once the specimen breaks, you need to note down the final diameter of the specimen. Similarly, final cross sectional area. Once you note down the diameter, from that you will get the final cross sectional area. Final gauge length. Already have made the punch marks on the specimen. Through this you need to find out the final gauge length. The member will elongate. Previously it was 90. Now the specimen is going to elongate. Now I am going to take this specimen and I am going to load it in UTM machine. The UTM machine, universal testing machine. I will explain the parts of the UTM machine. It consists of 3 parts. That is upper cross head. This is lower cross head. This is upper cross head, lower cross head, and this is the intermediate or middle cross head. And here grippers are provided. Here we are going to fit the specimen. Here we are going to fix the specimen. Here we have grips are provided. Through that it is going to load the specimen properly. After that, here we need to lock such that the hydraulic is going to apply the load on the specimen. For that, first you need to move this in the anti-clockwise direction such that you are going to apply the hydraulic pressure to the specimen. If you don't move this in the anti-clockwise manner, then you are not going to apply any load to the structure. If you want to apply the load on the structure, this has to be moved to the left hand side, and once you are going to on the machine, this is the switching on the machine, that is hydraulic on. If you want to off the machine, you have to use this right symbol, that is hydraulic off. And whatever the load you are going to apply on the specimen, initially you need to lock this. After that, once you move it to the anti-clockwise direction, the dial will show how much load is applied. And this entire setup consists of a hydraulic system. It consists of a piston and cylinder. As you increase the load, it is going to apply the pressure, or the piston will start moving. As a result of that, it is going to apply the load on the structure. And you can see that this is the screw column. It consists of 4 columns, 2 screw columns and 2 plate columns. This is the extensometer, which is used to measure the extension in the specimen. As I told you, when you are going to apply the load, initial extension in the specimen will be less, which cannot be measured through the machine scale. This is the machine scale. In this, it's difficult to note down the elongation in the specimen. For that reason, we are going to attach the extensometer to the specimen. If you see the extensometer, initially you need to adjust it to 0. Here you can see that I am adjusting it to 0. Both the dials I am adjusting it to 0. Now I have adjusted it to 0. Now you can attach this to the specimen, and once it reaches the maximum load, after that you have to remove the extensometer. Next, the readings will be taken through the machine scale. This is how the experiment will be conducted. Now in the next video, I will apply the load until the specimen breaks, and I will note down the values. I will show you how to take down the readings.
Conducting tensile test, 500 diameter tensile specimen, stainless steel material. Engage tensile specimen between crossheads. Apply extensometer to determine yield strength of material. After yield strength has been determined, remove extensometer and continue test to failure.
Students, have you seen that? That is also in the your I think strength of material lab, it will be shown. But for every property of, sorry, just a minute, sorry, 1 minute. So for the material, whatever we want to deform it, plastic and permanently, we have to test these yield strength and other part. And definitely we have to do this experimentation at elevated temperature to know that what will be the yield strength at elevated temperature. And on the basis of that, the critical decision has to be taken. that whether we are going for hot forming or cold forming. So the knowing these elastic and plastic deformation business and their values for the materials which we want to deformed for the bulk deformation process is absolutely important. And on the basis of that, the critical decisions taken. And once we are established with this process, we can manufacture for the world. And that whatever People's Republic of China is doing to go for huge quantity of manufacturing. First, they will produce it for their own market. And once this fixed cost and other things are justified, then maybe at the raw material cost or lower than that of the raw material cost, because you are a bulk negotiator, you just dump it throughout the world. So no competitors can compete with them because you are supplying the finished product at very, very low cost, even in a retail cost of that raw material, and you become the masters of the world in terms of the economy. That is why they have often $16 trillion economy, and most of the cases it is a manufacturing business. They are the manufacturing hub associated with that, and they very, very soon, maybe within 5 years, they will overpass the economy of USA. USA is basically a war economy. Whenever war is there, USA is relevant. And whenever steady state is required in civilization, China is relevant. And they're taking the full juice out of it to make their things happen. And many of the cases, China technologically far, far advanced. It's like, say, supercritical thermal power plant. None can compete with them in super thermal critical power plants and other things. They are the masters in terms of laying bullet trains in challenging terrain, like say Lhasa, to different parts of the vicinity of Arunachal. China is the only technology provider because they are doing all sorts of things in manufacturing associated with that. So let us conclude. We have discussed about the elastic and plastic deformation, which is absolutely important for the metal forming process. And we'll be working in a plastic zone. And we have seen some of the videos, how the tensile testing has to be carried out. We know that what is the yield strength, and on the basis of that will be applied for the judgment that how to deform it permanently in our own way. Sakshi? Who is there? Tanisha. Why there is so less presence? Today is also some class test?
Yes, sir.
Yes, sir.
That is the thing.
Take
Any
quiz.
questions?
Yes, so we
Okay.
have 2 quizzes in the evening, 5 p.m.
Okay.
and 7 p.m. So most of the
Okay,
students
okay. I understand. But I think that the attendance will be more in the second week, next week.
yeah, yes, sir. Like even in
Fine.
other classes, attendance is like this.
Okay. Okay, then. Tell me.
So what is the significance of the reason between a proportional limit and elastic limit?
Elastic limit means beyond that limit, the plastic region begins. Clear?
Yes. Yes, sir.
And proportional limit means that whenever stress is proportional to strain, beyond that, stress is not proportional to strain. And in elastic limit, there is some portion where proportionality is not there, but still it is elastic. Still it will come back, but in a non-linear way, not in the linear way. Is it clear?
So there will be, sir, offset.
No, stress, and I'm telling you, stress, and it will come back. It will come back to its original way, but there, after that proportional limit, if you increase the stress, the strain will not increase proportionally. That is the thing.
So there will be a plastic
No, I have told you, please try to understand. Proportional limit means up to that point when stress is proportional to strain. Clear?
Yes, sir.
Elastic limit means after that, when stress, the deformation, the strain will be permanent. So there is some region between proportional limit and elastic limit, where stress is not proportional to strain, but still it is elastic. Clear?
Yes, sir.
So that is the uncertainty where how you can model that. And after that, it will be permanent plastic. Then you will model that with that true stress strain curve. That means flow stress is equal to K into epsilon to the power n, and K and n are totally dependent on the material or metal properties. And we are interested about that because we want to material flow to take some form. So there will be a little bit of fluid-like character, because definition of fluid means flows, which can flow where negligible shear stress. And in the plastic region, you have less shear stress than the elastic region, so that you can deform material permanently. And that is our objective. Clear?
Yes, sir.
Any more questions? I always feel happy if I am critically asked questions. Maybe I will not be in a position to answer all the questions at a time, and maybe my knowledge is also limited. But that doesn't mean that I will not provoke questions from my listener. Otherwise, knowledge will not come. If you don't argue, if you don't debate, there is no progress. The dictators don't like debate. That is why they are stupid. All dictators are coward because they are afraid of questions. The teachers are coward who are afraid of questions. May not be. You are more intelligent than me. So you can raise some questions which I don't have the answer. But still it will provoke me for thinking. So questions should be asked. And through questioning, you will understand. The people who are questioning, that means they are thinking more than the people who are not questioning. So questioning is a measure of your interest and intellect. Thank you. Any more questions? My teachers were very good, but they don't provoke. That I learned that you have to provoke your students too, so that you ask questions, maybe embarrassing questions, which will expose my gaps, understanding in knowledge. But that is welcome. We will gain. The best defeat of a teacher if he is defeated by a student. I will win if I am defeated by you. I will not win if I am defeated by any other. But if I am defeated by my student, it is the greatest win for me. Okay, students, in spite of your busy schedule for the quizzes, thanks for taking part in the class. But the problem is that if the classes are missed, sometimes understanding, there will be gap. Not easy to plug in all those gaps. Still, thank you. Okay, bye. Prepare for your exam.
Thank you.
Thank you.
Thank you, sir.